In lesson 17, we're going to talk about alkanes. And I'm excited because this is the first of the functional groups we're going to discuss. Functional groups in organic chemistry are like combinations of Legos that you will use over and over for things. This is like the definite building blocks that really help you start to build molecules and understand their behavior by separating them into chunks and identifying what would happen in this area. Not a specific atom per se, but a collection of atoms that you learn to understand and recognize very commonly. And alkanes are a very simple version of that. I'm going to give you a few examples of them, starting with the simplest one. Methane. Notice it ends in ane because it's an alkane. Methane. We've talked about this a number of times, but just to hammer it, and assuming you're new to the video and never seen one of the other ones, meth means one carbon. There's one carbon here. Ane means that it's single bonded. Alkanes are carbons that are single bonded. The most bonded is a single bond. And that means that even if I have a big molecule, let's make something larger. Let's make ethane. Let's use ethane. And I'll write it out. Eth means two, and anes means single bonded. So see if you can guess what it's going to look like. There it is. That's it. That's ethane. Because you don't always write the carbon in, right? And you got hydrogen sticking off the edges here. I'm not even going to write the H's on it. That's ethane. How about propane? You want to take a guess what propane looks like? Well, it looks like this. Carbon, carbon, carbon. Look, I'm doing it for you this time. But that's propane right there. Prop means three. Propane. Ane because it's an alkane. All of the carbons here, the most bonded they are single bonded. This carbon has three hydrogens attached to it. But I want you to remember this one in the middle has two bonds. So he only has, or she, I suppose. Carbon could be a she. Two hydrogens attached to it. So keep that in mind as we're looking at these things. Let's look at another one. How about, let's see, here's methane. There's nothing for it to bond to carbon-wise, but ethane, propane, butane. Bute means 4, pentane 5, hexane 6, septane, octane. Here's octane, a common dominant molecule in gasoline. High octane fuel. This is octane right here. There's a couple of hydrogens sticking off every one of these. So there's some properties to these alkanes that I want to highlight that just they matter. These are described as saturated hydrocarbons. And it should be understandable why. Hydrogen plus carbon. Hydrocarbon. It shouldn't be a mystery to a chemist like you why we call it a hydrocarbon. The only thing in this molecule are hydrogens and carbons. But it's an alkane because they're single bonded. Carbon to carbon and carbon to hydrogen. Single bonds. And that means that it's the maximum number of possible hydrogens per carbon there are. That's the highest hydrogen to carbon ratio you can get. If I'm to double bond or triple bond, something like, why would I do that there? 2 carbons here. Well, there's only room for 1 hydrogen on each end like this. But this here is only single bonded, so he can have 3 hydrogens sticking off the end of him, and the rest of them have 2 here and here like this. So single bonded carbons have the most hydrogen bonding potential. Obviously, there's more room, more things for them to bond. Carbon always wants to bond to 4 things. Now, the ones that I've been drawing here are called straight chain alkanes. I could write a rap song about it if I wanted. But there are others. I could take, let's say, butane here, and I could pop a methyl group onto it here. Methyl meaning 1 carbon. Here's a CH3 here and a CH3 here. And this makes room for only 1 hydrogen left on this carbon. And this will have 2 hydrogens sticking off it, and this will have a methyl group on the end of it. So there's still lots of hydrogens here, but it's not a straight chain alkane. So if I was to write butane, which is what this is, it doesn't exactly highlight that there's this side chain going on here. And the way I know it's butane, we're going to learn naming along the way in these videos, is that we label the longest carbon chain we can, and it's 4 carbons here. You can see it would be 4 if I made this molecule number 1 also, but doesn't matter which one you choose, but here is 4, so I know it's going to be a butane. And then there's this side group here that hasn't been mentioned yet. So I can't just say butane, so what I do is I'm going to name it by the number it's attached to and what's attached to it. So I'm going to call it 2-methyl-butane. When a chemist reads this, they'll say, okay, it's a butane, and on the second carbon there's a methyl group attached to it. That's this guy here on the end. And that's the whole trick to it. We always want a number by keeping the number smallest where this kind of thing happens. So if I went the other way with it, let's say I took these numbers away and I wanted to go 1, 2, this becomes a 3 and 4. We don't do that because you want to keep the smallest number possible for wherever that's going to happen. So we would label from this direction this way here. But these are all alkanes, and their behavior is going to be relatively similar almost no matter what. And I'm going to show you a cool molecule. I'm going to take this right out of the textbook because I love it. This is going to be a picture of an animal fat. And look at the length of this carbon chain here. This is almost entirely hydrocarbon. If it wasn't for the double bonded oxygen here, we would actually call it an alkane, but that's all it takes for it not to be one. But if you notice, this huge chain of carbon, 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 carbon here has H2s on it, because alkane, it looks like this. It's got dozens and dozens of these. There's only room for 2 hydrogens here because this carbon is attaching to 2 others substituents next to it, right? So that's what you're looking at here. That's what this animal fat is, with the exception of this oxygen that's over here. But 98% of the mass of this molecule are these long straight chain alkanes. And that's really interesting. So now you should have something of an idea of what a fat is. It's almost entirely hydrocarbons, which the body uses for energy, breaks them apart. We'll talk about that at a later time. But I just want to point out that not everything is a straight chain alkane. We call the others branched chain alkanes, and we'll call them branches or whatever. So like, let's say we have butane. Let's bring butane back up like that. Well, there's another thing that's like a butane, like this, and they actually call this isobutane. But that's a misnomer, because the real name for it, if you want to use the convention we just talked about, let's label it 1, 2, 3. So I'll label it 1, 2, 3 like this. This would be 2-methyl propane. Prop meaning 3 carbons, ane meaning single bonded propane. And this methyl group is not part of that. So it's why we have to label where it is. And we often call it isobutane. That's a common naming convention because there's 4 carbons in there. And isobutane can act a lot like regular butane, even though it's actually a propane. It's because the number of hydrogens you're going to come across, well, I'll let you count it. You can discover what that looks like. But it's important to understand that there are all kinds of combinations, especially the longer you get, like C6. I love this statistic. C6H14. That could be 1, 2, 3, 4, 5, 6 hexane, right? And you get 3 hydrogens off the end here. And you get 2, 2, 2, 2. That should add up to 14. Because the way you know is that you take the number of carbons and you multiply by 2 and then you add 2. Because there's 1 extra on each end here where there's no more second carbon bond, and you get 14. But you can actually draw 5 different isomers. Isomers is what we call it when they have the same chemical formula, C6H14, but a different configuration. Maybe it's one shorter this way and has a chain this way, or maybe it's out here, or maybe it's here. But it's all C6H14. It's 6 carbons saturated with hydrogens. And 5 isomers may not sound like a lot, but look what happens when I increase the size of my formula. Just C9H, let's see, 9 times 2 is 18 plus 2, so there'd be 20 hydrogens on this. You could do nonane, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's nonane. But I could just as easily take a couple of these away. Let's take this away here like that and just add a carbon this direction and a carbon this direction. And now this becomes 2,3-dimethyl septane, but it's still 9 carbons and 20 hydrogens. There's 35 valid isomers that still produce this chemical formula. And if I want to get crazy with it, just to give you an example here, if I want to write a formula for C30H62, maybe I just have 30 carbons in a row like this. I can't even take the time to draw it out. I can tell you, though, that there are 4.1 billion combinations of C30H62, and they're all valid. They're not just going to necessarily be straight-chain alkanes. In fact, only one would be. The odds of drawing it are worse than winning the lottery 3 times in a row. But because we're learning about the behavior of alkanes, we can assume that all alkanes will behave somewhat similarly in similar conditions. And we can use that information to pay attention to what we think would happen, say with one form of fat versus another form of fat. They should have almost identical behavior. If we look at our functional groups and we pay attention to the behaviors we learn about hydrocarbon alkanes, then we will be able to apply it to all 4.1 billion. We don't necessarily need to keep track of all of them, though we will play with one in the next video. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.